Everybody, it's Video Notes 10.1 coming to you live from Sheridan Avenue. So, 6 bullet points we're going to look at today. And so here we go. Please read 2 chapters, chapter 15 and also chapter 7. Just those sections, you'll see some cool pictures and try to understand it. So, what are we talking about? We're talking about solutions. So, water is rarely pure, but often a solution. Solutions are homogeneous mixtures. Okay, very well mixed, so well you can't tell one part from another, except that they each keep their identity. You could have lots of types of solutions, but all solutions have 2 parts. The solute, the smaller part. The solvent is the biggest part. The thing that solute gets dissolved, you get dissolved. You get dissolved. All right, that's how I remember it. You solute get dissolved. Solvent is the bigger part that does the dissolving. Miscible is a particular term for when 2 liquids mix. So water's a liquid, vinegar's a liquid. If you mix 2 liquids, it's called miscible. Okay, so some types of solutions. Alloys are solid solutions of metals. Solid and liquid, oh, we got that one. Liquid and liquid miscible, things like alcohol and water, vinegar and water, those kind of things. Gas and a liquid, carbonated beverages, and gas and a gas. Take a deep breath in, and you just breathe in a solution of gases. Check it out, Diet Coke. All right, so question 1, will it dissolve to make a solution? So how can we get will solutes dissolve? That's what we're looking at. So what dissolves? Polar things dissolve polar things. We have to go back to when we did polarity of molecules, all right? All of these cancel out, so this is non-polar. So it does not qualify for this. No, all right? Since it's non-polar, it would dissolve other non-polar things or be dissolved by non-polar things. Look at this, H2O, pretty polar. So would something dissolve in water? Well, let's see. This, whoops, sorry, wrong way. This is also going to be polar. Partial negative, partial positive. So these 2 things would mix, yep, because they're both polar. All right. Ionic things dissolve in polar solvents because they have positive and negative. Positive and negative. All right. And polar is opposite charge. Ionic is positive and negative. Nonpolar dissolves in nonpolar, and polar does not dissolve in nonpolar. So what do you think, ChemCat? Oh, that's cute, your little joke. And that's cute, little polar bear. And what can you say about the Wicked Witch? All right. She said she was melting, but I don't think that's true. I think she was dissolving, and she had water thrown on her. So what can you say about the Wicked Witch? Translation. All of those things mean this. Like dissolves like. It's a very rule for dissolving. So go back to last slide and see if you can use like dissolves like to understand. All right, dissolving. Well, when things are dissolving because they're polar ionic, it's because electrostatic attraction. Polar things have opposite charges, opposite sides. Ionic things have opposite charges and opposite sides. So that's why those things dissolve in each other. If something has no charge, it has not much attraction for each other, kind of like dispersion forces. Okay, so why do nonpolar things dissolve in nonpolar if there's no charges to attract? Well, there's no repulsion, so they mix. There's a little bit of attraction due to London dispersion forces. So if you had a dry cleaning solvent that dissolved nonpolar oils, well, nonpolar, then it must be a nonpolar solvent. Okay. Butanol dissolves in polar water. What does that tell you about butanol? It tells you that butanol is polar. Or ionic, but it's not ionic. Okay, question 2. So that was question 1. What will it dissolve? Question 2, how does it dissolve? All right, so we know if things dissolve in each other, but we don't know how. So the solute and the solvent make a solution. The solute and the solute are stuck together by whatever kind of force is holding them together. Sugar has something holding it together to be sugar. The solvent bonds break when a solution forms, and so because water is held together by bonds, okay, hydrogen bonds, and then the solute solvent bonds form to make the solution. Okay, so we have a little outcast to help us with this part. All right, keep listening. Some ionic compounds don't actually dissolve. Okay. Why not? So we just said Ice cold, baby. We should have listened to this one last time, all right? Okay. Just a little outcast right in the middle of the PowerPoint. So how many dates does it... So, okay. We just said ionic things dissolve in polar. Okay. But some ionic things don't dissolve. So why not? Well, look at this happy couple. All right. Happy, happy, happy couple. All right. So you would have to have a lot of energy to break apart the happy couple. And if they're ionically bonded so tightly that even water doesn't overcome that force, then they're going to be insoluble. Okay, so some ionic compounds have a stronger attraction for each other than they do for water. Okay, these guys obviously are also so attached to each other that they won't dissolve in water. But many, many ionic things do. We'll talk about it in a second. But remember these? Whoa, solubility rules. Okay, and we found out that lots of things are soluble and some things are insoluble. Okay, and this is because soluble things are more attracted to the water than they are to each other. Insoluble things are more attracted to each other than they are to the water. All right, so what's the difference between ionic and molecular? Well, molecular compounds could be polar or they could be nonpolar. If they're nonpolar, probably not going to dissolve in water. But if we, oh, here we go with the sugar again. Sugar again, all right? Sugar dissolve in water. All right? Solid sugar, aqueous sugar. No breaking down, except for this song. They're breaking down. All right. Aqueous. But look, a whole molecule. There we go. Let me some sugar. That was the whole part. All right. So you take some sugar into water and it dissolves. But what happens is that water surrounds each molecule of sugar, but the sugar stays whole molecules. All right. Because they're polar, they're surrounded by water. So what's it, a dissolving equation for molecular compounds? Well, here's some molecular covalent, same thing. All right, so we look at this and we say, wait a second, this is C's, H's, and O's. All right, it's called methanol. It's a liquid. Is it going to be miscible in water? You betcha, because it's polar. So you CH3OH, and it's aqueous because it's surrounded by water. It's solvated. NH3 is ammonia. It's a gas, and it's polar, so it dissolves in water. What happens when it dissolves in water is every ammonia molecule gets surrounded by water molecules because they're polar. Okay, how is that different than ionic compounds? Well, ionic compounds not only dissolve, they dissociate. Okay, they don't just dissolve; they dissolve and they dissociate and turn into their ions. So if NaCl dissolves in water, you get Na plus ions and you get Cl minus ions. And they're not connected anymore. So here's that happening. Here's the negative ion surrounded by the positive side of water. Positive ion surrounded by the negative side of water. Okay, so ionic compounds have what are called dissolving equations, and they show the ions as products. So there we go. We start with solid sodium chloride. Well, it dissolves AQ surrounded by water, aqueous, but notice it breaks into two pieces, into the ions. That's different than those molecular. They stay together but get surrounded. Okay, all soluble ionic compounds break up into their ions. Okay, here's another thing that you have to know. It's called the net ionic equation. It shows the opposite thing. Some ionic compounds don't dissolve in water. They precipitate when those ions come together. So a precipitation or a net ionic equation shows the ions that were in solution, but when they find each other, they make a precipitate or a solid. Okay, so dissolving equation turns into ions. Net ionic equation turns into a solid. Okay, so here's some examples. Check it out. It's calcium chloride, metal, nonmetal, soluble. So we get the calcium ions, aqueous, and 2 of the chloride ions, aqueous. Why did I put the 2 in front? Because when this breaks up, it breaks up into Cl minuses, but there's 2 of them. All right. Here we have the magnesium ions, plus 2, get your PT, and then 2 of the nitrate ions for every magnesium nitrate that dissolves. These are dissolving equations because they show the solid breaking up into its ions. Okay, when water attacks, here's 2 pictures. I'm going to show these in class. I'm going to have you decide what kind of solute is dissolving in each of these 2 pictures. Okay, so I'll leave that for the class. All right, so another way to tell if an ionic compound or a molecular compound dissolves is to see if it conducts electricity. What is electricity? Movement of charged particles. Ionic compounds have ions that can move when you put them into water, so they can conduct electricity. So they're called electrolytes. Hey, you might have heard that before. What gives you electrolytes? That Gatorade and the Powerade and stuff, because they have ions in it. Molecular compounds do not conduct electricity because they don't break up into ions, so they're called non-electrolytes. So look, this solution has no ions in it, no light bulb. This solution has some charged particles in it, so you see the light bulb on. This has a lot of charged particles and they're surrounded by water. So there's the, whoopsie, erase that. So you could have the negative side of water surrounding the positive ions, and then the positive side of water surrounding the negative ions. And you get many ions, and that's a good idea. But okay, so question 3, can we make it dissolve faster? I think you might know this one. If you want something to dissolve faster, what can you do? Well, you can stir it. You can increase the surface area, grind it up, or you can heat it up. Those are 3 ways to get it to dissolve faster. Faster. But faster does not mean you can get more to dissolve necessarily. Okay? So this is how you make it dissolve faster. But that doesn't mean you can dissolve 5 cups of sugar into 1 drop of water. Okay. Oh, here's something else we could talk about. Soap. Yay. Use soap. All right. It helps dirt dissolve. How? Soap has a polar end. Look, it charges. All right. And soap has a nonpolar end. Look at all this nonpolar carbon chainy stuff. All right. So there's a hydrophilic end, likes water. Hydrophobic end doesn't like water. And so it can get water and dirt to mix. And then the dirt comes off your hands. Yay, finally. All right, question 4, how much can dissolve? All right, so this is the term for how much can dissolve. The maximum amount of solute that can dissolve in a given amount of solvent at a given temperature is called solubility. Get that definition down, all right? So we can describe different solutes by how much they can dissolve in a given amount of solvent. But it is temperature dependent. Temperature does affect solubility. So if something's warmer, it'll probably dissolve more solid. So that can make more. So warming a solution can make it hold more solute. But and then also for gases, if you warm up a solution with gases, it would hold less solute. Less gas dissolves in a hot solution. Pressure affects solubility, but only of gases, all right? So higher pressure, higher atmospheric pressure, more gas dissolves. Less atmospheric pressure, less gas dissolves, okay? But there's no effect on dissolving using pressure, pretty much. No effect on how much dissolves. Okay, so how can we describe solutions if they're saturated? They can be saturated, which means full of solvent. Sorry, I said solvent, I meant solute. Look, it's a saturated bucket of KFC. You got it full. Unsaturated means unfull of solute. You could still get more solute in that bucket. I mean chicken, or do I? All right? And check out this big old piece of chicken. That bucket is holding more chicken than it should. That's super saturated. It's holding more solute than it should in normal life. Okay? So don't forget the chicken. All right. So how do we describe that numerically? Well, we can make a graph. All right? So this graph is the solubility of the substance. Solubility means it's a saturated solution. The line represents a saturated solution. Okay? Why is that line changing? Because the temperature is changing. So you can get more of this substance, KNO3, to dissolve. If you heat it up, more dissolves. Cool it down, less dissolves. Okay? This line is called a solubility curve, and that's a saturated solution. Okay? So at 20 degrees, you can get, what, about 45 grams 45 grams of KNO3 to dissolve. At 60 degrees, you can get about, 110 grams of KNO3 dissolved. At 85 degrees, you can get a whopping 200 grams of KNO3 to dissolve. Okay. What else can you see from a solubility curve? Oh, it's the sugar again. Yay. Yeah. So we got some sugar dissolving, all right? If you're right here on the curve, it's an unsaturated solution of sugar because you can get this much more to dissolve, right? If you're on the line, it's a saturated solution of sugar. Okay, so if we have 150 grams of sugar at 150 grams of sugar at 20 degrees, it's below the line, unsaturated. 250 grams of sugar at 40 degrees, it's right here. That is above the line, so only this much will dissolve and this extra amount will sit at the bottom, not dissolve. All right, not dissolved. It's the extra, all right? So it is saturated and there's stuff sitting on the bottom of that solution. Okay, supersaturated can be made. What does that mean? That means you can have a solution that is holding this much solute at that temperature, but you can't just put it in at 30 degrees and make it dissolve. That won't happen. So how can you make it? Okay, you heat up water, you saturate it, and it has a bunch of solute. If you cool it down slowly, the extra solute should fall out, right? Go right to the bottom because it can't dissolve. Usually it does, but some solutes don't do that, and now the cooler solution has too much solute, so it's called supersaturated. It's a fragile system, and often the extra precipitate can fall out pretty easily. Okay, so how do you make a supersaturated solution of NaClO3 at 40 degrees? Well, here's its solubility curve. There's its saturation line, right? So we can heat it up and add a lot of solute and get it to dissolve there. But then if we take that all dissolved solute and cool it down, when we get to here, we would expect to start seeing solute fall out. But if the solute stays dissolved and cools nice and slowly, then we can get to 40 degrees and maybe still have that much solute dissolved. That would be supersaturated. Okay. All right. So when the solution that's supersaturated precipitates out, it looks like it froze, but it really didn't. We'll try it in class. Okay. So how do you test if a solution is saturated? You add a crystal. Okay. Something can happen. If you add a crystal to a saturated solution, the crystal will not dissolve. All right, it'll go to the bottom. It won't dissolve. All right, in an unsaturated solution, the crystal will dissolve. Okay, and in a supersaturated, solution, the crystal will cause lots of crystals to precipitate because it was holding too many crystals in the first place. All right, we'll see some examples. Please read the book. And let's let Outcast take us out. Remember, solution is a homogeneous mixture. Solute is the small part. Solvent is the big part. Supersaturation is an overachiever. Polar dissolves polar and ionic. Okay, nonpolar dissolves nonpolar. And just for your own benefit and my public service announcement, use soap. For real. Peace out.